Hi, good evening. Am I audible? And is the slides visible? Any one of you? Okay. Kindly ask the rest of the students to join as soon as possible because uh, you know we have to keep the track of that attendance and all these throughout meetings, right? So please ask them to come as soon as possible. Please inform them. There are only 26 people right now. 27. Remember, for the final year guys, we had a notification today that the presentation will be held online and everything should be kept under record, right? So even if I try to breach these things and if they ask for the presentations and all these recordings, it will create a lot of problem, right? So please ask the rest of the students to come up as soon as possible. At least they can join me in the next half an hour also. Shall we begin? We left up with this table and two of the problems that we have solved, right? Now, we have even talked about the tautologies, that is, when respective the values of p, if the propositions are against true. We talked about the contradictions, that irrespective of the value of p, if the proposition is always wrong, that means false, then it is called as contradictions, right? And we also have a kind of hybrid situation. We call it as the contingencies, right? In case of contingencies, we do have the or operator for p and q. And here, p, the irrespective of the value of the p and q, it can hold both true as well as the false conditions, right? Now, there are two more terms here. You have already known it, but still, antecedent and the consequent. Something in a very broad sense is something that is in front. That is the front part of the proposition. That means the if clause. We call it as the antecedent, and something that comes later. That means the conclusion part. We call it as the consequent. That means the if clause is the antecedent, and the then clause is called as the consequent, right? So in our case, we do have p as the antecedent, and we do have the q as the consequent. Little disturbance in voice. Okay. Argument. The bird is a crow, therefore it is black. Is it okay? Can you hear? Or still there is some kind of issues? Is it okay, Hassan? Okay, fine. Now, see, you don't have to remember everything. I'll be just highlighting the things that you're supposed to know. Definitely, you're supposed to know it. So, if you're keeping a piece of pen and paper, that thing will help you out in just jotting down some of the very specific and important points. Let's say, like this whole of the slide, we do have the discussions on argument, right? So whenever we do have the conditions for argument, there are two there are two very specifically important things that are there. The first one is the premise, and the second one is the conclusion. Now, what is this premise? Premise is something that provides the ground, or it provides the evidence, or in fact, it provides actual evidences for saying or asserting something. And what is this conclusion? Conclusion is something that is on the basis of premise. If it is coming to, or if it is coming down to a point of conclusion, that means it is deducing something from the premise that has been already provided. We call that segment of the information, that segment of the assertion that is there, we call it as the conclusion, right? So, for example, that bird is a crow. therefore it is black. So what is the premise here? That since the bird that is there, that means it can fly, we can have some of the other facts also associated with this compound sentence or complex sentence, that the bird can fly, or it has got feathers, and with that we have given one more premise, that is the bird is a crow. Since the bird is a crow, it has to be, the conclusion is that it's black, right? Now there is one more thing that you're supposed to know. Like, when can an argument be valid, right? What are the conditions for an argument to be valid? Argument has components like premise and the conclusion, but under which cases the argument is valid? Argument is valid if and only if its corresponding conditions are is a tautology. That means it is either, it can be a tautology, that means irrespective of the value of p or q, it is always true, or the two statements are consistent. That means there is no contradiction cases. That means the assertion or the proposition that has been provided to you either holds a true value for all cases or holds a false value for all the cases, but neither, under any condition, it should not hold the condition of true and false in the same situation, right? And the two statements are logically equivalent. That means I do have a double implication, or I do have the equivalence operator. Whenever I do have the equivalence operator, I call it as the logically equivalent. So for an argument to be valid, I need to have three conditions. It must be a tautology, it should be consistent, and it should be logically equivalent, right? Now comes the predicate logic part. We have dealt this thing very precisely in our lectures, so let's not waste time out here. They just talk about certain examples. We have solved these things, right? That all men are mortal, and Socrates was a man, and Socrates is mortal. All these things, what are the predicate part of it, and what are the deductive evidences? We have gone through forward chaining and backward chaining. We have solved many of these, right? So we are gradually moving forward. Then they talk about the predicate representations. That means Judy runs. There are small predicates that are already there. These things were previously also there in our slides. In that the car that Tom is driving is blue, the sky is blue. That means we are putting up the format of X is blue being a predicate, and we're just adding up the subject part in front of it, right? So these all things you have already gone through. We should not waste much of time. This is the part where predicate logical expressions has been dealt with, and we are having certain operators that are shown. The example out here is that you can see it here. Obviously, with the operators of lesser than, that means 3 lesser than 2, or 2 is less than 1, and we do have the 1 less than 3 under all the cases. This is a false one. So this is how we are using these operators and all. They've just given a small example for this. You have to just run through these slides once. Now, predicate logic quantifiers, you have already gone through all these things. That means we do have the well-formed formulas, and those well-formed formulas have got certain logical quantifiers. Those logical quantifiers are what? Now, there are two kinds of logical quantifiers in any of the WFFs, that means well-formed formulas, and we've already known them. They are basically what? Now, they are basically the universal quantifier and the existential quantifier, right? So in this case, x greater than 5 cannot be a proposition because we don't know the value of x out here. In the declaration part, that means how we used to say that for all x, where x is something, that is the statement associated with it. They have just talked about this, where q can hold a value of a universal quantifier or a existential quantifier. Any of these things can be there in the place of x, and the remaining things, as we have already known, goes, right? We have just shown the part of it, and we have already dealt with all these things in our classes. There's something that I have said in the cues, universe of discourse, right? Like the best thing is, it indicates, what does this thing, universe of discourse, indicates? A set of entities, or in some cases only entities, or the whole of the universe, or the propositions in all as a fact, right? So the best way to understand is about natural numbers. So for all x and y, there is some of the condition that has been given. There is no need to be more precise to say something that for all x and y in n, that means within the natural number boundary, which we call it as the universe of discourse. Here in this case, n is implicit. That means n is not stated in all conditions, and it is presumably understood that n belongs to the universe of discourse. That means the larger set, right? The larger set to which it belongs. Fine. Now, applying the universal quantifier, that means for all, they have just shown this thing, how we do apply it, like x for all x. That means for all the objects, x is in the universe of discourse, right? So all cars have wheels, that means for all x, where x does have cars, that means x does have wheels, that means cars does have wheels, right? Likewise, we do have the existential quantifier part out here. We'll be saying someone loves you, that means there exists an x who loves that particular individual, right? So we've known all these things. There is something we call it as the formula building, right? In case of formula, like defining recursively as variables, constants, and functions, generally we convert any set of given problems into this form, right? Where f is an n-array function and there are symbols ranging from t1 to tn, where n is the arity of the terms, right? Generally, we call them as the atomic formulas. That means the smallest set of formulas. Here, we have all the definitions of it. Atoms are thus the simplest well-formed formulas or the simplest WFFs. Right? We also do have compound formulas. And compound formulas are found by combining the atomic formulas with the logical connectives. And finally, after we do have the atomic formulas and we do have the compound formulas, combining both of them, we do have the WFFs or the well-formed formulas. They are basically the assertions of or propositions of complex sentences or compound sentences taken up together, right? Now, here they talked about T1 and T2, where T1 and T2 are the terms that are involved, right? And R is a relation symbol comprising which holds the all the terms starting from T1 till Tn. And if I call that not of A is a formula, then obviously A is also a formula. Now, A or A and B and A or B are also formulas based on A and B, right? And we do have a set of compound formula examples that has been in front of you. You can see there are a lot of connectives and operators that are involved. There are a lot of connectives and operators with precedences that are given to this formula, right? The precedence is given by the braces as well as the operators. And about the precedence, we already had the table in our last lecture in which we talked about the precedence of all the operators that has been already given to you. Next comes the representation of is an instance relationship, right? So we already have had a very long discussion on is an instance relationship. In this case, they have simply said that how things can be represented for a particular proposition. That means if we are taking the example of Joe is a musician, then we are calling Joe as an instance of the class of things we call it as the musician, right? So Joe plays the role of an instance and the musician plays the role of a class. We have already discussed about what is instance and what is class during our sessions for frames and semantic nets, right? And then this has been pictorially shown out here. Now we'll be talking about the computable functions and predicates. Now, what are these computable functions and predicates? Let's say we do have a problem, and that problem has to be converted back into the predicate class of problems, and then how are we going to deal with it? Just a moment. There are a lot of people who are waiting in the lobby. So, computable functions and predicates, right? What do we have here? Like, for example, we'll be seeing one of the problems. We have got two problems. The first one is that of the calculation of the factorial, and we do have the second one, the conditional expression for the triangular functions. Now, in the first one, what we are going to do here is, let's say, excuse me, we are supposed to find out the conditional expression for the factorial of n, that is n factorial, we have to calculate. Now, what are the things that we need to picturize in this problem? The thing that we are supposed to picturize in this problem is that we have to have certain propositional expressions. We call them as the P1, and then we do have the consequent part, that is E1. So if there is P1, then we do have E1. Else if we do have P2, then we do have E2. Else if we do have Pn, then we do have En, right? So P1 implies E1, P2 implies E2. This is the form in which I need to get my problem, right? So here what you're doing is we are just seeing this n factorial where n is 5, right? We are having n here, and then the next one is n minus 1 factorial for n greater than or equal to 1. So how we are breaking it up is 1, 2, 3, 4, and 5, and we are getting out 120. So in all the cases we already know this part of the fact. So this whole of the thing starting from here to here can be somehow summarized as, just a minute, a lot of people waiting. Thus, the above conditional expressions to define the functions of n factorial can recursively can be stated as that if I do have n factorial out here, then it will be comprising of propositional expressions like n equal to 0 implies 1 and n not equal to 0 implies n into n minus 1 factorial. Likewise, this thing will be further divided into n minus 2 and will be going unless it goes up to either less than 1 or 0, right? Now here let's evaluate 2 factorial. 2 factorial is all about, I'll be just writing this in this particular formula's form, right? So what we are doing for 2 factorial here is 2 equal to 0 implies 1 and 2 not equal to 0 implies, that means it is the extension part of this factorial for going to the 1 factorial, right? So 2 into 2 minus 1 factorial. So here it comes up as 2 into 1 factorial. Now I'll be forgetting this part. I'll be writing this as we wrote 2 factorial by applying this formula. I'll be writing, just a moment. Right. So I'll be writing this as 1 equal to 0 implies 1 and 1 not equal to 0 implies 1 into 1 minus 1, right? So now I'll be left up leaving this part, and now I'll be computing 0th factorial by the application of this formula again recursively. And what I'll be doing here is 0 equal to 0, it implies 1, and 0 not equal to 0 implies 0 into 0 minus 1 factorial. So this thing will automatically become now 1, and we cannot further proceed. So we do have 2 into 1 into 1, or basically it is 2 into 1, that is 2. Right. Likewise, we'll be solving this particular problem by the application of this formula that has been given to you, and this has to be applied recursively, right? Now comes, there is one more term called as the resolution. How to remember resolution? Please, in your group, kindly notify that it's come up on time. Okay, every time I have to go there and I have to allow people from the lobby, it makes quite a lot of difference, right? It makes quite a lot of difficulty. Now, while we are talking about the resolution part, resolution in one statement, if we try to remember it, resolution is about proving something by application of contradiction, right? Resolution is about proving something by use of contradiction. That means by applying contradiction, if I'm proving something, I call it as the resolution representation, right? Resolution is also referred to as resolution is a rule of inference. Resolution is a computerized theorem prover. And these all things are there, like theoretical concepts you have to go through. Now, we do have the KR knowledge representation using rules. Whenever I do have a knowledge representation using rules, they comprise of the production rules, and sometimes they have the semantic net and frames. But basically, here we'll be considering the production rules with the if, then, and else conditions that are there. So, if condition, then the action, or if there is a premise, then the conclusion. If the structure is somewhat like this, then we call it as a rule-based system or production-based system. We have talked about what rule-based systems are there, what rule-based systems are, because they comprise of the working memory, they comprise of the rule base, and they comprise of the inference engine. We'll be talking about all of them today itself and its application part. Now, the types of rules. We do have, obviously, we have known it many a times, like declarative rules and the procedural rules. We do have one more, that is the meta rules. Let us see what are these. In case of declarative rules, some assertions are made straight away, like if the inflation rate declines, then the price of the gold goes down. Now, in case of inference procedure rules, what happens is some of the data may not be provided, right? In case of declarative rules, straight away information is given and I come down to a kind of a conclusion. But in this case, I may not be having the data that has been clearly provided to me, and I can request it from the user, or I can deduce it even further, right? To solve these kind of problems. Whenever we talk about the meta rules, the third one, we talk about rules within rules, or making out rules from the previously given rules or provided rules. So meta rules reason about which rules should we consider for firing. In this case, the best example is out here. Just listen to it. If the rules which do not mention the current goal in their premise part is what? No, the part that is in front of the proposition, right? And conclusion part is the rear part of that particular assertion. So, if the rules which do not mention the current goal in their premise, and there are rules which do mention the current goal in their premise, then the former should be used in preference to that of the latter, right? That means I have to use this one in place of this one. Why? Because these rules' production part, that means its consequent part, straight away takes us to the goal. So I can immediately supplement these to the previously given premise and consequent part, and I can deduce the overall problem to its goal state, right? Just a moment. Now, again, no repetition of these things, procedural versus declarative. Rather than going through all these things, it is better to see the comparison ones, right? You have already known it, but still. In case of procedural knowledge, it is hard to debug, and in case of declarative knowledge, it is easy to validate. In case of procedural knowledge, we do have the black box. In case of declarative knowledge, we do have the white box for it. In case of procedural knowledge, the things are basically obscure, whereas in case of declarative knowledge, it is very, very explicit. In case of procedural knowledge, it is basically process oriented, whereas in case of declarative knowledge, it is basically data oriented, right? Now, in case of procedural knowledge, the extension may affect stability, whereas in the declarative part, it is extension is easy. Now, basically, procedural knowledge is fast, whereas declarative knowledge is a little slow. They are basically simple. Procedural is simple, whereas our declarative is a little high level, right? They are basically represented in the form of set of rules, whereas they are in the form of production systems, right? There is another comparison on the basis of an example. That means they have taken up the language, C++, Python, etc. That is procedural, whereas they talked about another declarative language, that is the SQL. And the similar things that are there in our previous slide, they have been discussed out here in these cases. Kindly go through it of your own. Okay, fine. In case of logic programming, from here, we'll be giving a little bit of idea about the prologue part, right? But we'll just be defining certain things which you have already gone through in your strawberry prologue, right? we'll be talking about the representation, we'll be talking about the data that it holds, we'll be talking about the logical implications that it holds, we'll be talking about how the things are asked, that means the question pattern also, right? So in case of logic programming, we do have the logic program, we do have the programmer, and we do have the computation that is to be kept in mind, right? Basically, logic plus control in case of Prolog are the algorithms that are given, right? Now, examples of logic statements. A grandparent is a parent of a parent. So, if a person is a grandparent, a person is a grandparent when? Now, if she or he has a child, and that child is also a parent. Right? So, this thing is written as for all x, where x is a grandparent of y, and this is another rule that has been provided, right? So this is how things will be dealt with. Yeah, in case of Prolog, we do have certain data components. We do have certain data components. The data components in Prolog are like data objects, that means the terms. They can be simple or structured. The simples are further subdivided as constants and variables, and the constant as atoms and numbers. Now, the data objects like constants, they can hold these values, whereas variables, the important thing is this one, that means compound terms. In case of compound terms, we do have one very important thing that you're supposed to know is a functor, right? What is this? Now, functor comprises of a function f with an arity of n for all its arguments that are there. What are these arguments? These arguments range from t1 till tn, and this n part is nothing but the arity of the functor's argument that has been given. So you have to just remember this part. Now, ground and non-ground. The terms are ground if they contain no variables, otherwise they are non-ground. Fine. Now, simple. This is how numbers and variables they are represented in Prolog. No more discussions on this. Now we do have the structured data objects. They just talked about the general structure of it. We do have the special structures when you do have more than one subject and predicate parts, right? Now comes the program components. We do have the clause, we do have the predicate. Like here, cows eats grass, subject is cow, and the predicate is eats grass. Simple things, right? More important part is out here. Here, an individual x. This is nothing but the interpretation part. It's nothing but the interpretation part. Like an individual x is a grandparent of z if a parent that same x is y and y is the parent of z. So they are talking about x is a parent of y, right? So y is the son of x, and then z is again a child of y. So in these cases we can say that x is the grandparent of z. Likewise, there are certain other facts like being the mother of one of the individuals being the mother of another individual, and one of the individual being the father of another individual. They have all been categorized on the basis of what? On the basis of their individual belongings, right? Now, unit clause. You have to just remember one fact. What is a unit clause? Unit clause is something which has got a true value in all conditions. See, in Prolog, the clauses that are unconditionally true are called as the unit clause or a fact, right? There are certain examples that are given to you out here. Yes, there is something that is there in the query part. Like you got a query Q, and you're asking who's the grandparent of Z. So this is the Prolog representation of it. You've still seen it in the strawberry Prolog part. Then you do have the programming paradigms. Have got three programming paradigms. The model of computation. Then, then you do have the imperative models. Imperative models are the models of computation which consists of a state and an operation of an assignment. This is imperative model. We do have a functional model also. They basically consist of a set of values. Functions, and operation on functions. You have to just remember these parts, nothing more. And then comes the logic model. In case of logic model, there are logical computations that are involved. So you need to just remember the logic model. You have to remember what is the functional model, and you have to remember what is the imperative model, right? Now, here, from here you have to pay a lot more attention. Here, just pay a little attention. Like, to determine the mortality of Socrates, and thus we have been provided with certain facts, rules, and certain contradictions. For the first time, we'll be including the term called contradiction out here. So, in our first statement, that means 1a, what do we have? Now, Socrates is a human being. This is a fact that has been given to you. Now, again, there is another rule that has been provided. This is an assertion, right? This is a predicate assertion that has been given, or this is a proposition that has been provided to you. Now, if X is mortal, then X is mortal if X is human, right? X is mortal if X is human. What is the assumption? A deliberate assumption has been given. Now, Y, there is another individual Y who's not mortal. Then under all the cases we need to understand that Y cannot be human being. Now I am assigning X equal to Y. That means I am assigning something who's a human and a mortal to Y. Under these cases, what's going to happen? That means now I can say that Y is not human from 2 and 3 by unification of modus tollens. Modus means repetitive rule assignment, right? Repetitive rule assignment. So now I can say that Y is equivalent to Socrates, and from 1 and 4 unification, we can say the contradiction is that by using 5, 4b and 1, 5, that means Y is Socrates, 4b, Y is not a human, and 1, I can say that there is a contradiction, right? What is the contradiction? Contradiction is that now the contradiction that comes up is either Socrates is not human, and if he is human, then he cannot be mortal. But since Socrates is Y, and Y is not mortal, so there is a kind of a confusion state that what Socrates is all about. Okay. So this whole explanation has been provided out here. They are now defining the forward versus backward reasoning. Now remember, this is not exactly the same that we talked earlier, right? Here we'll be talking about conflict resolution and the conditions of the conflicts that arises during forward as well as backward reasoning, right? Forward chaining is about data driven. They are basically data driven, whereas backward chaining, it is basically goal driven, right? Now we do have an example in front of you. Rule number 1 is we are provided with a few rules. Rule 1, Rule 2, Rule 3. Rule 1 says if it is hot and smoky, then definitely there is a fire, right? Rule 2 says if the alarm beeps, then it is smoky. Now, Rule 3 says if there is fire, then switch on the sprinklers. Fine. Now, if this is there, then there are certain facts. That means certain extra addition of information that are given other than the rules that are in front of you. What are those facts? Now, alarm beeps. This is given. Fact 2 that has been given is it is hot, and this is also given to you. This is one of the examples. Now, uh, in case of forward backward chaining, there is some more thing that can be done. Like I do have the set of rules and I do have certain instructions that are given. The instructions are these part. So if the premise is this, then you have to add this further information to the working memory part. Let me tell you, this is our rule base. This and this are rule base. This is one, rule two, rule three is our rule base, and this fact one, fact two is my working memory. That means I'll be gradually adding up what has been said on the basis of the premise that has been given to me. I'll be adding up further informations to my working memory part. That means out here. So the alarm beeps that is given and further informations can be added. Let us see how we can do it. Like there is a typical example for forward chaining that has been provided to you. I do have the rule R1. Rule R1 says if it is hot and smoky, then add fire, right? Then add means don't add fire. That means they're talking about you can add a further fact that is fire. Now, if the alarm beeps, then you can add another information that it is smoky. Rule 3 says if there is fire, then add another fact that is switch on the sprinklers. Now, in this colored part, we do have the set of rules ranging from R1, R2 till R3. And now after that in the working memory part, I do have two more facts. Two facts that has been already provided to me. What are those facts? Now, the alarm beeps and it is hot. These are given to you. That is the facts that are given or provided. Just a moment. Right? Now, what are the extra facts that can be added? The extra facts that can be added are if you start skimming from the first rule towards the third rule by including the already provided facts, that means F1 and F2, you can deduce further more, or you can infer further more informations. What are they? Now, in case of fact 4, this has been generated, right? This has been generated or added. How did I add this fact 4? Now, from F1 and R2. From F1 and R2. What you can do here is, rather than skimming through all of them, pick up the fact that has been already given in your working memory part. That means alarm beeps. If alarm beeps, then you have to add smoky. So what we have done here is, in case of fact 4, we have added the term called smoky. Now pick up this second fact that has been given, that is already there in the given part, that means F2. Now here, if it is hot and we have generated another fact. So hot and smoky, that means F1, and R2. Sorry, by F1 and R2. By F1 and R2. So here I'll be coming up to hot and smoky, that means F2 and F4. So F2 and F4, by using F2 and F4, hot and smoky. So I'll be searching out, is there something in the premise part of it? Yes, hot and smoky is there. So if it is hot and smoky, then I have to add fire. So I have not only used the fact 2 and fact 4, right? Fact 2 and fact 4 is not the only thing. I have also used R1, that means rule 1. So I have got this fire out here. Now, since I have already generated these, now what is your task? You will be again skimming through this, and this. That means there are two facts that are given to you, and there are two more facts, F4 and F2, that has been generated by you, that has been added to you, that has been added by the already provided rules into the working memory part, right? So if you just go through them one by one, then what you can get is, by using F2 and R3, by using F2 and R3, F2 and R3, what you can do is, if there is fire and if it is hot, then add the switch on the sprinklers, right? F2 and R3. Yes, if there is fire, then You could have asked me a question. Then these things should have been. You could have changed. This will not be. This will not be F2. This will not be F2. This is F4. This has to be F5, right? This will be F5 out here, right? Now, there is another case of typical backward chaining. Now, in case of backward chaining, what are the things that are there? Now, here I'm not asking, or here the rule base is not asking you to add something. The rule base is not asking you to add something. Rather, what has been done here is, you do have the first rule. If it is hot and smoky, then it is fire. If the alarm beeps, then it is smoky. And if there is fire, then switch on the sprinklers. And there are two facts that are given to you. That means if it is hot and and the alarm is beeping. So my goal state is now to prove or to answer to a question, that is, should I switch on the sprinklers? Right? This is there. So we'll be seeing now the basic structure of the forward chaining, right? The basic system architecture of the forward chaining mechanism. Now, the forward chaining mechanism generally do have a rule base, and they do have a working method, and they do have an inference engine. Now, how can you see them out here? This is the rule base that you do have, right? This is the rule base part that you do have. In the rule base part, you will be having these rules. The working memory initially is fact 1 and fact 2. Initially, it is fact 1 and fact 2. By application, that means a fading difference is there, a fading out, a very thin line difference is there as we are moving from the provided facts, and by application of provided facts with the already given rule, if I am reducing something, I call it as I am inferring certain more facts. So in this diagram, you do have the rule base and you do have the working memory, and gradually by use of rule base as well as by use of working memory, the user is now getting the actual facts. That means he is inferring more and more facts. So here you can just go through. Facts are held in the working memory. The condition action rules represents the actions to be taken when specified facts occur in the working memory. Typically, the actions involve adding or deletion of the facts from the working memory. You could have asked me a very important question out here that, okay, fine, facts are getting added. What do you mean by deletion of the facts? What do you mean by the deletion of the facts? By the way, I just want to ask you, I'm audible, na? And you can see the slides, na? You're understanding, na? Any one of you? Okay, fine. Take it, it's fine. Okay, I'm just taking up a sip of tea, huh? Yeah, just for a few seconds, I'm just taking up a sip of tea, right? And then I'll be again explaining it. Right? I haven't even taken a full minute also. Okay, now properties of forward chaining. All rules which can fire, do fire, or should fire, then can be inefficient also and leads to spurious rules firing, unfocused problem solving in case of forward chaining. So these are some of the properties which you should remember. Now let us very precisely see what is the forward chaining algorithm. No. I should give some more ideas on this fact. Deletion of the facts. What do I mean by deletion of the facts? In all our problems that we have dealt previously, what we used to do was we had certain rules, we deduced certain facts, and we added them to the working memory. And this thing went on, right? And this thing went on. But there are certain situations that may arise in case of forward chaining specifically. when the necessity of deletion of facts is becomes essential. Now, why does this deletion of facts becomes essential? There is a very straightforward answer to this question. Deletion of facts is always, kindly remember, all of you, those who are here, deletion of facts are always related to the contradictions that arises, or deletion of facts are always related to the conflicts that arise. Now, you might be thinking that how can conflicts arise under these situations, right? So, we'll be seeing it out here. Even before we move any further, we'll be just going through the forward chaining algorithm. How does it go? In a very simple senses, you have to repeat this whole part. That means first you have to collect rules whose condition matches a fact in the working memory. You have to collect all those rules, the same thing that we have done previously. We have to collect the rules whose condition matches with the fact in the working memory. That means you have to catch hold of those rules which has got relevance with the working memory. That means alarm beeps, it is there. So I'll be catching hold of rule number 2 and I'll be adding another fact to the working memory, that is smoking, and that is what I have done in case of fact 4. I'll be catching another term from the working memory, that is hot, but I could not add anything further here, so I'll come down and I'll be going to the working memory again. Hot and smoking is there, and from rule 1 I have added fire. So coming down here, collect the rules whose condition matches a fact in the working memory. Do actions indicated by the rule. That means add something that has been given in the premises conclusion part. So I am adding something to my working memory. Do actions indicated by the rule. In the rule you can see do this or add this, it is there. What we'll be doing is we'll be adding the facts to the working memory or delete the facts from the working memory also at some of the occasions, right? Now let us see the extension of the example number 2. We have got two more rules out here and one more fact that has been given. There's one problem out here. You could have said it as F3. This thing could have been or should have been in fact F3. So now rule number 1 is hot and smoky, then add fire. Rule number 2 is alarm beeps, then add smoky. Rule number 3 is fire, then add switch on the sprinklers. Now remember, the moment I do have a simpler premise, that means fire is there, then switch on the sprinklers. If it is straight away dry, then switch on the humidifier. See, these are simply contradictory. That means if there is fire, there will be sprinkler. If it is dry, then there will be humidifier. Humidifier will be adding moisture, whereas switch on the humidifier since it is dry, and fire is also there, then switch on the sprinkler. They'll be adding water to the fire that is there. Now, if the sprinklers are on, then delete dry. That means if there is a sprinkler, I cannot have the situation that is dry. I cannot have a situation that is dry. Okay? So now I do have a set of facts. Earlier, what are the set of facts that I was having? I was having alarm beeps that was there, that has been provided, was given. And the next one was it is hot, and this was also given to me. One more fact that was added was I do have a dry one, right? A fact, another fact is there. That means I do have a dry condition also. This is fact number 3. Even though you can consider it as fact 2 also, there is no issue because my conflict part will not be affected whether I put up the fact number, whatever fact number I'm putting up. Let us see what happens here. Now, what am I going to do here is I'll be R4 will be cross-detected, right? How come? दिव्यांशु गर्ग क्या कर रहा है? दिव्यांशु अपना अपना माइक ऑफ कर दे बाबा। कहाँ है रे? So now, by using what? Now, rule number R2 and R4. By using rule number R2. Why R2? Now, from the working memory, I have picked up alarm beeps. So, while coming down from here, I have picked up this rule R2, and I have added Smoky out here. So, I have added Smoky out here. This thing could have been here. There's no issue. Now, I do have the second one. Hot cannot be used out here because hot with Smoky can be used. Instead of that, I'm using fact number 3, which is written as F2. That means dry. So since I do have a dry fact that has been given in my working memory, I am adding switch on the humidifier. So now after Smoky, I do have addition of the humidifier that is on by using whatever facts that are I'm saying you, they are already provided to you in the braces. Now I do have the fire. The fire comes from F2 and R1. F2 and R1. I do have the R1 hot and R1. F2 and R1. That means hot, and this I am adding up what? Now I am adding up the fire out here. Now the moment I do have the fire, that means now I'll be considering this fact, this fact, this fact, humidifier, Smoky, and this. The moment I do have a fire, I can put on this switch on the sprinklers. So this fact has been added, that means switching on the sprinklers. The moment I'll be having switch on the sprinklers, that means the moment sprinklers are on, I have to delete something. Not only addition, I have to delete a fact. That means now dryness cannot exist, right? Since the sprinklers are on. So the moment we have added this fact out here, there is a conflict. That means we have to delete dry. That is, the humidifier is off. Okay. So this is how the conditions of contradiction or conflicts arise. So now we'll be modifying this already provided algorithm, and we'll be adding up a few more segments out here. Now see, the forward chaining algorithm now can be modified as repeat. That means we have to repeat all these steps, collect the rules whose conditions matches facts in the working memory. We have already done it in our previous algorithm also. Now if more than one rule matches as stated above, that means if more than one rule matches as stated above, then we have to use a strategy for conflict resolution to eliminate all but one. That means I should have only one condition that holds true, and there is no conflict out here. And there is no conflict out here. So do the actions as indicated by the rules. That means keep on adding the facts to the working memory or delete the facts from the working memory. How long you have to do it? Now until the problem is solved and no condition match exists, right? So now what you're going to do here is, there are certain, since we talked about the conflict resolution strategy, we need to know what are the conflict resolution strategy. The first and the foremost thing is you have to remember these three terms: refractory, recency, and specificity. What is the literal meaning of refractory? The literal meaning of refractory is stubbornness. That means getting stuck up with a particular fact, right? Getting stuck up with a particular fact. That means you have to get stuck up with a particular fact. Recency. Recency comes from the term called being recent or being more fresh. Specificity. That means something related to something being very specific, right? So refractory is one of the terms you need to remember. Recency is one of the terms that you need to remember, and specificity is another term that you need to remember. So the conflict resolution strategies in refractory, a rule should not be allowed to fire more than once on the same data. That means you have to check out here that whether the rules are getting fired again for the second time, because until unless a rule gets fired, as in this case for the second occasion, you cannot get a conflict or a contradiction, right? So refractoriness talks about this, and you have to discard the executed rules from the conflict set. If it has been already used, you have to discard that particular rule. Then comes the recency. In case of recency, the rank instantiations in terms of the recency of the elements in the premise of the rule will be used. That means you have to check which one is more recently used in the premise part of it, not the conclusion part of it, and how quickly or how recently this has been used. You have to keep it, and if something is coming up at later stages, that means you are picking up some of the facts from the working memory, and that working memory is fact in correspondence to some of the rules. If it is coming at some later stages while you are scrolling down in case of forward chaining, then that thing may be discussed. This is one of the rules that you can adopt, right? So recency is one of the rules that is there. Now the second one is the specificity. Specificity is a rule which does have a greater number of conditions, and rules which have a greater number of conditions and are therefore more difficult to satisfy are preferred to more general rules with a fewer conditions. Why? Now you could have thought of that rules with a fewer conditions can be used first. Rules with fewer conditions means, see, if it is fire, then add this. If it is dry, then add this. If it is sprinklers, then delete dry. But rules with this is a rule with more than one condition. That means hot and smoky. Then only you can add a fire here, right? So this specificity, recency, and refractoriness you have to remember, right? Then alternative to conflict resolution using meta knowledge. आप इस स्लाइड को पढ़ने वाले हो. Then you have the backward chaining system. You have to just go through this diagram. You have to prove a goal G. It is in the initial facts, right? So I'll be switching on the sprinklers if there is a fire, and the alarm will beep only when there is a fire as well as it is smoky, then only alarm will beep. Or else if there is only fire, then it will be the condition of hotness, right? It will be warmer. Simple encoding rules, nothing is there. A small difference between forward and backward chaining depending on the problem. Control knowledge, references. So we are done with our knowledge representation part. Next lecture we'll be starting with a fresh topic, and we have to finish it in the coming 1 week. So Agam or Harshit, any one of you, Agam and Harshit, both of you, just take up the screenshot of the attendance, please. Please don't go. Please don't go. There are 63 people. Agam and Harshit, both of you take up the screenshots for the attendance, please. And keep it as today's date and px, right? ऐसे करके आपको रखना है. प्रीवियस वाला भी आप लोग रखे हो, है ना? हो जाए तो kindly send me in the chat that you have already taken. हाँ भाई, हो गया. Have you taken the attendance? Arshit, Agam, हो गया. Okay, thank you, and bye. Take care. If acha, tell me, can we meet tomorrow for 1 hour, even though it is Sunday, and if you don't feel the pain, can we meet for 1 hour? Rest of the guys kindly say, don't say it forcefully, huh? Can we meet for 1 hour tomorrow? Time maybe जब आप नींद से उठ जाओ अच्छे से, like maybe around 10 or 11. चलेगा? 4 p.m. शाम को. अच्छा अच्छा, देख लेते हैं. 11 बजे के बाद एनी टाइम रखूं, 11 या 12 के बाद एनी टाइम रखूं. लंच का टाइम डिस्टर्ब नहीं करूंगा, मे बी 11 से 1 के बीच में, या फिर अराउंड 4. 5 में थोड़ा सा प्रॉब्लम हो जाता है. आई फेस सम प्रॉब्लम एट 5. रीजन बीइंग, आई एम स्टेइंग एट ईस्टर्न इंडिया, राइट, वेरी नियर टू बे ऑफ बंगाल, एंड there are heavy rainfalls out here, and we do have a lot of thunderstorms, and all these things happens after 4 or 5, and it becomes very problematic. Okay, fine. I'll be deciding something after 1, and I'll be notifying. Okay? Kindly see the Facebook group for that. Thank you. You may leave and enjoy the evening. Thank you. Bye. Take care. God bless.